Discover the hidden symmetry of nature. How a uniform boundary ensures that complex forces always return to a state of perfect equilibrium. This mathematical narrative begins with a concept of perfect balance within a physical space. Imagine a curved surface, such as an orange hemisphere, sitting atop a flat, circular boundary. When we study how two different scalar fields interact across the surface, we find a remarkable rule. If the first field remains exactly the same value all along the boundary curve, the total sum of their interaction over the entire surface will always be zero. The core logic of the proof. The reason for this vanishing result lies in the relationship between a surface and its edge. When the first field is constant at the boundary, it effectively loses its power to influence the total sum, allowing us to focus solely on the second field as it travels around the closed loop of the edge. Because the second field is a gradient field, meaning it represents the slope or rate of change of a value, returning to the starting point of a loop means the total change must be zero. It is like hiking up and down a mountain to return to your exact starting spot. Regardless of the path you took, your net change in elevation is nothing. Visualizing the equilibrium. This principle is brought to life through interactive 3D demonstrations. In one simulation, blue arrows representing the interaction of these fields are plotted along the circular rim of a hemisphere. The constant scenario. When the first field is uniform along the rim, the blue arrows arrange themselves in a symmetrical pattern. A central green arrow, which represents the total sum of all these vectors, collapses to zero. The variable scenario. If the field is changed so that its value varies along the rim, this symmetry is shattered. The blue arrows shift, the balance is lost, and the central green arrow grows, representing a non-zero result. Real-world physics. The no free lunch rule. This mathematical certainty is the foundation for conservative forces in physics, such as gravity or static electricity. A force is considered conservative if the work it does depends only on your starting and ending points, not the path you take. A second demonstration illustrates this using a particle moving along a figure-8 path within a gravitational field. As the particle moves downward, the force of gravity does positive work, adding energy to the system. However, as the particle swings back upward to complete the loop, it performs an equal amount of negative work. Because gravity is a conservative force, these two sides perfectly cancel each other out by the time the particle returns to its start. The importance of the result. If this total were not zero, the world would work very differently. A non-zero result over a closed loop would mean you could move an object in a circle and indefinitely gain energy, creating a perpetual motion machine. This mathematical proof confirms that as long as the underlying fields are balanced at the boundary, the system remains closed, and no net energy or work is created out of nowhere. Whether through 3D visualizations of hemispheres or animated particles on a track, the conclusion is the same. Symmetry at the boundary leads to total equilibrium.